Good morning. Thank you for joining MDMR today as we host industry experts Aaron Burke of Pacific Biolabs and Jeff Sauter of NewTek Corporation. Aaron managed a sterilization program for 5 years for a laboratory consumables company, and Jeff Sauter brings 15 years consulting experience within the medical device and biotech sectors. He's accredited by the Association of Medical Instrumentation, Radiation Sterilization for Medical Devices. Pacific Biolabs and NewTek work closely together to perform microbiology and sterilization for medical device sterilization validation programs. Today, Jeff and Aaron are going to share their expertise and advice on how to ensure successful validation, which is a key factor in successful device development program. Today we'll be discussing the connection between bioburden and sterilization with 6 key topics and points. These are bioburden, what it is and how it can affect device development program and sterilization validation programs. Sterilization, methods and bioburden sterilization connection, benefits of minimizing the sterilization dose for your device, the importance of monitoring bioburden. They'll also be covering a case study, sterilization failure and tracking down the root cause. Last, they'll be covering how to monitor and reduce your bioburden levels. Now, before I turn the meeting over to Aaron, I'd like to draw your attention to the chat window on the right side of your screen. Please use this area to enter your questions, which we will address upon the conclusion of our presentation. Thank you again, everyone. Here you go, Aaron.
Thank you, Anita. So one of my personal goals today for everyone is to make sure that by the end of this webinar, all of you listening will think of determining bioburden and performing sterilization validation testing as an important earlier stage process for a medical device or sterile lab product. In fact, if your device will need biocompatibility testing data, the FDA strongly recommends that biocompatibility testing be done on the device in final form after sterilization, because sterilization has the possibility of altering the materials of a device, which could change its biocompatibility profile. Determining device bioburden and developing a sterilization plan at an early stage can help avoid costly delays. Fixing a problem earlier in the process is typically less costly than fixing it once you've discovered a fundamental flaw in your design or process. Of course, nearly everything in device development is important, and you probably hear that a dozen or more things are all priorities at once. But bioburden and sterilization is one area we feel doesn't get the attention it deserves, especially among smaller companies or less experienced device developers. Of course, that being said, almost everything in the early stage of developing a new device can seem like its priority. Developing a device is difficult. It takes skill, coordination, and fearlessness. It's like juggling cats. Before defining bioburden and talking about how we measure it, I think it's important to briefly go over the steps involved in the sterilization validation program. First, you must determine the bioburden of your product. This number will guide you in the amount of sterilization needed for your device. Simply, the higher the bioburden, the greater the sterilization dose needed. Think of it like washing your hands. The dirtier your hands, the harder it is to clean them. Really grimy hands covered in grease will need a lot of cleaning. It's the same with bioburden and sterilization. Next, you must select your sterilization method, typically gamma radiation, electron or E-beam radiation, ethylene oxide, or steam sterilization. Today we'll be talking mostly about radiation sterilization, so the processes we'll describe reflect that. Then, you sterilize your device at a verification dose, which is determined by your initial bioburden number, which is much lower than the dose your products will see in production. You then check those devices for sterility. If everything passes, your sterilization validation is complete and validated. This process ensures that when you finally sterilize your products, they do in fact end up sterile and safe for use. But once you perform this validation, you're not done. You will need to periodically check your bioburden levels on future lots of production to see if anything has changed, and will also need to verify that your sterilization dose is still effective. This is very important, and later in this webinar, Jeff will talk about why it is so important. And of course, our ultimate goal here is to develop and deliver an effective product that is safe to use. Now, to get us to a really solid understanding of bioburden and its role, first, let's define it. And I've written out this whole definition here, which I don't normally like to put on a slide, but I think it's actually really important, so I've put it out here for everyone to be able to read. The definition is, the bioburden test determines the total number of viable microorganisms in or on a medical device, container, or component. It is performed on any product that requires control and/or monitoring of bioburden counts, usually as part of a sterilization program. This test acts as an early warning system for possible production problems that could lead to inadequate sterilization. It is also used to calculate the necessary dose for effective radiation sterilization and to monitor product routinely as part of a quarterly dose audit. What this means is that you need to know bioburden early. A higher bioburden, meaning lots of microbiological organisms are on your products, means that a high sterilization dose is needed to ensure that the microorganisms are killed. So you need to know the bioburden in order to figure out the amount of sterilization required. And you also need to know and regularly measure bioburden during manufacturing to see if anything is starting to go wrong. For instance, something introducing a high level of microbes to your devices. If the bioburden rises significantly, your sterilization dose may no longer be effective in fully sterilizing all products, and you can end up with non-sterile devices being sent to market, which I think we can all agree is bad. Now please understand that this entire process can be complex, and I'm simplifying it somewhat, but in short, it's important to realize that bioburden is not a test your product passes or fails. It is information that helps us deliver a safe product. From our definition of bioburden above, we have the term viable microorganisms. Let's talk about what those are. In general, we're speaking of bacteria as well as fungi. Typically, fungi are yeasts and molds. The ones we obviously are most worried about are the ones that can cause harm to humans. Examples are the yeast Candida albicans, which is especially harmful to immunocompromised patients. The mold Aspergillus niger, one of the most deadly molds to humans. Some strains have been known to produce large amounts of aflatoxin, which is a toxin and a carcinogen. Exposure can cause allergic reactions and/or infections in patients with immune system deficiencies. There are a few bacteria that we tend to worry about. E. coli is gram-negative bacteria that lives in the mammalian gastrointestinal tract. Most strains of E. coli are harmless, but several can cause food poisoning in humans. You may have heard of food recalls due to E. coli contamination. Pseudomonas can cause sepsis and is most common on medical equipment, which we definitely want to be sterile before use in surgeries. And Staphylococcus aureus is a source of staph infections. MRSA, which is becoming more and more common, is a methicillin-resistant strain of Staph aureus. These microorganisms can come from several sources during production, including the air and particulate matter in the air, handling by humans, contact with non-sterile surfaces, such as tables, bags, and molding equipment, and contact with liquids, which can be particularly dangerous as liquids are more likely to harbor bacteria, and this can lead to endotoxin contamination. Bioburden can also come from previous use of a device on humans. Now, though we're focusing today on single-use or terminally sterilized devices, it is still important to understand that significant contamination can occur if reusable devices are not properly cleaned and disinfected or sterilized prior to reuse. The FDA is finally making a strong push to ensure all device reuse procedures have been validated, which is a very good thing for patients. An extreme and very unfortunate example of what can happen with non-sterile devices occurred recently at UCLA. Endoscopes were not properly sterilized after use, leading to the deaths of 2 patients and to the potential exposure of more than 100 other patients to antibiotic-resistant carbapenem bacteria. While this is an extreme case and involves reusable devices, it does highlight the importance of proper sterilization and the role bioburden can play. Now that we all have a good understanding of the importance of bioburden, let's talk about how to determine your bioburden. This information can be found in the standard ISO 11737. First, we have to validate the specific method we have chosen for our specific device will work with that device. This process is called recovery. To perform this, we inoculate 3 sterile or near sterile devices with a known quantity of microorganisms. So we don't want the devices to have any microorganisms existing on them when we start. After inoculation, we recover the microorganisms and see what quantity or percentage we have recovered. We need to ensure that we are able to recover a sufficient portion of those microorganisms, or the method will not work and is not valid. We also obtain a recovery factor in this process that is used in calculations to determine product bioburden. 2 examples of device features that can affect recovery are 1, antimicrobials on the device, which can kill microbes, lowering recovery, and 2, device geometry. Crevices, for example, can make it hard to recover inoculated microbes. Once we've validated our method through recovery, we can then determine actual device bioburden. This involves culturing what is on the device. Basically, we're looking to see what amount of microorganisms were present on the device by allowing these microorganisms to grow in culture media. Applying the recovery factor obtained previously, we then calculate a number for bioburden, which is expressed in CFUs or colony-forming units. A very important aspect of this process is that samples for bioburden must be gathered from the lot to be tested or from representative lots if multiple lots are to be tested. No special sampling methods should be used, and samples should have gone through all steps of the production process. Now, to give some idea of the amount of samples needed for bioburden, if we were performing bioburden for products that would be produced frequently or continuously and in large quantities, so more than 1,000 devices per lot, we will need 10 sample devices from 3 separate lots. If you're making smaller or infrequent production batches, then we will perform bioburden just on the 1 lot, so 10 samples are needed. Once bioburden is known, we can then move on to the next steps in a sterilization validation program, which Jeff will now go into for us.
Thank you, Aaron.
Thank you, Aaron and Anita. Hello, everybody. And in addition to the bioburden study and the bioburden recovery as addressed by Aaron, there are also microbiology testing components of a sterilization validation that include the BF test as well as the sterility test. The bacteriostasis fungistasis test is used to validate the sterility test, which is also known as dose verification. Some devices, including devices that have antibacterial coatings, possess properties that inhibit the growth of microorganisms. The purpose of this test is to show that nothing in or on the product inhibits the growth of microorganisms, which can lead to false negatives, thus misinterpretation of the sterility test. For the BF test, product is processed at a typical irradiation sterilization dose, typically at 25 to 40 kilogray, and then product is then inoculated with the known numbers of bacteria culture and fungi culture, then incubated. Any product that shows no growth or slow growth is considered bacteriostatic or fungistatic. If this is the case, subsequent tests are needed to compensate for any inhibiting effects to determine the method modifications that are needed to overcome this inhibition. Next is the verification dose or the sterility test. And the verification dose ensures sterility. The verification dose, also referred as sterility test, is performed to verify that the irradiation dose as determined by the bioburden portion of the validation is effective in killing the microbial load and sterilizing the product. For the verification dose, product is processed at a sublethal dose, which is typically for irradiation sterilization under 10 kilogray. This sublethal dose requires a sterility assurance level of 10 to the negative 2. And it is also conducted to ensure that there are no radiation-resistant bugs on the product. A SAL level of 10 to the negative 2 means that there is a 1 in 100 chance that a device will not be sterilized based on the microbial load of the product. For ISO 11137 method 1, the dose is designed to deliver a 10 to the negative 2 SAL level, and for VD Max method, the verification dose is at a 10 to the negative 1 dose level. Once the verification dose is completed, dose from this test is used to establish dose required in order to sterilize the device to a SAL level of 10 to the negative 6. This means that the probability of there being a viable microorganism present on the device must be equal or less than 1 in a million. Assuming that the sterility test passes and all standards are met, the process is validated. Next, we will cover the different types of sterilization validation methods for irradiation sterilization per ISO 11137. There's VD Max in method 1, as well as method 2 and method 2A, which are incremental dose methods, which we will not get into today, but we will address VD Max in method 1. VD Max and method 1 are the most common sterilization methods used for irradiation sterilization. Method 1 is used for product that is manufactured in higher volumes, and VD Max is used for product that is manufactured in lower volumes or devices that have high manufacturing costs. The microbiological testing is the same for both methods, but the difference is for method 1 that 100 devices are required for the sterility test, and for VD Max, 10 devices are required. For the full validation sterilization, for the Bioburden test component, the product is required from 3 separate manufactured lots for Bioburden testing. Now, if a product is manufactured in separate lots, say like every 3 or 4 months, or if there are anticipated design changes that are anticipated to the device, then a single lot release sterilization validation may be a better alternative to the full sterilization process. The reason is that with any validation, a quarterly dose audit is required for 4 quarters ensuing the sterilization validation for that device, or for manufacturing lots, whichever is more frequent. The advantage of a single lot release validation is that the second and third lot validations can take place of the quarterly dose audit that is required anyway, and any design changes can be validated as part of the second or third lot release. For the full validation process, a total of 149 devices are required for method 1, and 49 devices are required for VD Max. The Bioburden study requires 10 devices from 3 separate lots. For method 1, as mentioned, 100 devices are all from the same lot are required for the sterility test, and for VD Max, 10 devices are required. And then there are also additional devices that are required for BF testing, bioburden recovery, and verification dose map. In conjunction with the sterilization validation process with the devices that are used for microbiology testing, there are also devices that are required for a dose map study. And this requires 2 full or complete shippers of product that will be intended for routine sterilization processing. While the dose map study is separate from the validation itself, and it is usually run concurrent with the validation process. The dose mapping process plays an important role in the overall sterilization validation process, as it establishes how tight of a dose range the devices can be processed at. Processing product in as tight of a dose range as possible, or DUR, along with low bioburden levels, establishes a low validated dose, and are key determinants in optimal sterilization processing particularly of complex devices and sensitive materials. A full sterilization validation typically takes 8 weeks to complete. This is inclusive of a protocol, microbiology testing, all irradiation processing, and the dose map study, and also the final report, which gets submitted to the FDA along with the 510K submittal. Next, we will address the most commonly used forms of terminal sterilization. Basically, there's primarily ethylene oxide, gamma, and E-beam. X-ray is also emerging as a practical technology, particularly for combination devices and those type of materials. Ethylene is basically a gaseous process or irradiation sterilization, split pretty much half EO and half irradiation. Ethylene oxide and irradiation sterilization are the most commonly used forms of terminal sterilization. Most devices are processed via ethylene oxide, about 30% gamma, and about 15% is processed via E-beam. While ethylene oxide and gamma are dominant methods, combination devices and devices containing sensitive materials demand a more innovative approach to the sterilization of complex devices. When applied correctly, ethylene oxide, gamma, E-beam are all safe and effective technologies for sterilizing medical products, each having its own advantages and disadvantages. For example, product containing Teflon or acetal or devices that contain active electronic components are best suited for ethylene oxide sterilization. Gamma is very penetrating and commonly used for sterilization of high-volume disposable medical devices and is the best option for materials of high density such as surgical drapes. However, ethylene oxide and gamma are facing increasing regulatory and safety threats, and there is a growing trend within the medtech and biotech industries to look at sterilization as an integral part of device development in optimizing throughput and device performance. While both gamma and EO sterilization are recognized and accepted by regulatory bodies throughout the world as providing safe and sterile medical devices, these technologies have certain deleterious environmental consequences and to the devices themselves. EO is routinely used for gaseous sterilization of disposable healthcare products and medical device manufacturing. Its high penetration rate and potency of microbial kill proved to be an excellent technology for sterilization. However, ethylene oxide leaves harmful residues that are carcinogenic to humans. Also, long aeration times are needed to make these products safe for human interaction, and these aeration times cause supply chain complexity. Gamma is a no residual safe alternative to ethylene oxide sterilization. However, due to its high penetration energy, the process has a tendency to cross-link materials, particularly plastics. And particularly with complex devices and sensitive materials, E-beam affords versatility and flexibility in customizing processing techniques, allowing for optimizing sterilization throughput and efficacy of the device. Trends show a shift towards E-beam because of reduced product degradation and specialized processing requirements for complex devices. With E-beam, a beam of high-energy electrons directly destroy bioburden. These high-energy electrons collide with other electrons, and these secondary electrons have an energy adequate to destroy bioburden as well. E-beam delivers a dose rapidly, typically under a minute, and this protects a product's function. Because of E-beam sterilization very short exposure times, its radiation effects on materials, especially polymers, are often measurably less than those caused by gamma processing. The combination of shorter exposure times and improved DUR, which is dose uniformity ratio, enables customers to make E-beam an attractive alternative to gamma. Now, the limitation of an E-beam is that it cannot penetrate highly dense materials as can gamma. While E-beam and gamma sterilization methods are employed widely in the medical device industry, X-ray is not as well known. However, despite its lack of exposure, it combines the best features of both gamma and E-beam, melding E-beam's rapid turnaround times and processing flexibility with gamma's high penetration capability. In addition, X-ray provides a more even dose distribution than gamma. X-ray is a new developing process that is based on obtaining X-rays or photons through conversion of electron beams. X-ray sterilization offers a better penetration characteristics than either gamma or E-beam techniques, and they have the same penetration properties as with gamma, but the treatment is faster, more flexible, and more environmentally friendly. X-ray offers excellent penetration and sterilization and delivers a dose, much more even dose distribution than either gamma or E-beam. As a note, NewTek Corporation will be opening a new facility in Fremont, California in November of this year, and we will be expanding into X-ray sterilization in addition to E-beam and EO sterilization capabilities. Now, radiation is radiation. If you stand in the sun for 5 minutes, it'll cause modification to your skin. That is a fact, and you want to minimize the damaging effects of irradiation. While irradiation sterilization is among the most popular and well-established processes for sterilizing polymer-based medical devices, it has long been known that these techniques can lead to significant alterations in the materials being treated. High-energy radiation produces ionization and excitation in polymer molecules. These energy-rich species undergo dissociation, abstraction, and additional reactions in sequence, leading to a chemical stability. The stabilization process, which occurs immediately after, or even days, weeks, or months after irradiation, often results in physical and chemical cross-linking or chain scissioning. All materials have been found to break down at very high radiation doses. However, the range of doses under which a given plastic will maintain its desirable properties depends greatly on the chemical structure of the polymer itself. Indeed, below the destructive level of exposure, radiation treatment can impart many benefits and enhance properties of commercial value. While in some cases material modification is desired, for example with cross-linking and chain scissioning, cross-linking, for example, of balloon catheters, in other cases material changes can include embrittlement, discoloration, odor, stiffening, softening, or enhancement or reduction of chemical resistance, and an increase in or decrease in melt temperature. Understanding how and to what extent these characteristics can be altered as a function of the level of the radiation exposure is crucial to predicting the performance and utility of irradiated plastics. The influence of radiation on the properties and performance of a polymer differs according to whether the material degrades or cross-links, and this in turn depends on specific sensitivities or susceptibilities inherent in the polymer backbone. In both gamma and electron beam irradiation, available oxygen is quickly consumed within the polymer. However, in the case of E-beam, the time of energy application is so short that before more oxygen can permeate into the material from its external surfaces, the application of radiant energy has been terminated. the direct formation of additional radicals ceases, and the stabilizing chemistry pursues alternate, less degrading routes, such as cross-linking. In simple terms, the chemistry changes as a result of starved chemical reaction, similar to how a fire goes out when the oxygen is consumed in a closed container. In gamma radiation, the application of ionizing energy continues over a much longer period of time, allowing reactants such as oxygen to permeate back into depleted areas of the material, resulting in a greater degree of chain scissioning. Damaging effects of oxidation, such as discoloration, can be reduced by polymer additives or copolymers that, especially in the presence of certain other additives, can help minimize radiation damage to plastics. These compounds are frequently termed anti-rads and are generally substances that also act as antioxidants. They function either as reactants, combining readily with radiation-generated free radicals in the polymer, or as primary energy absorbers, preventing the radiation's interaction with the polymer itself. Discoloration, usually yellowing, is caused by oxidation activation of chromospheres or color centers in the polymer. And this discoloration can often be mitigated through the use of antioxidants, differing processing temperatures, or a selection of a higher molecular weight polymer. Now, back to the point of benefits of low bioburden and its crucial link to sterilization. Especially with combination devices and sensitive materials, the link between low bioburden and optimal sterilization processing is no greater. Devices are typically processed in a 25 to 40 kilogray range, and for a sensitive device, processing a device at a range of 20 to 30 kilogray, for example, can make the difference in successful processing of a device via irradiation sterilization. If a device, on average, across 10 devices from 3 separate lots, averages 45 CFUs or less, the product could be validated at 20 kilogray, at 9 CFUs or less. It could be validated at 17.5 kilogray, and at 1.5 CFUs on average or less at 15 kilogray. And techniques, in addition to validating your product at a lower dose level, requiring, of course, low bioburden, with E-beam and X-ray, you can optimize sterilization of sensitive materials with advanced techniques. E-beam offers the flexibility to introduce or implement customized or specialized techniques that could be validated and incorporated into the routine sterilization processing of that device. When developing a device, it is important to think about sterilization options from the design phase, as some materials are not compatible with all methods. And combination products bring a greater compatibility issue to any sterilization task. It is vital to conduct testing early on to prove out the suitability of a chosen method on materials. Because each polymer reacts differently to ionizing radiation, it is important to verify that the maximum dose likely to be administered during routine sterilization processing will not adversely affect the quality, safety, or performance of the product throughout its shelf life. Experimental tests of the product should include irradiation at least to the highest dose encountered during routine sterilization processing. Since various device applications call for certain performance properties or functional characteristics, it is important to test each device in an appropriate manner. The selection of materials for radiation sterilization should start with the following basic rules. Most medical products are durable in radiation. Using the highest molecular weight materials, materials with the narrowest molecular weight distribution that is optimal for irradiation sterilization. Aromatic materials are more radiation resistant than aliphatic materials. Higher levels of antioxidants improve radiation resistance. Materials with low oxygen permeability are more radiation resistant. And avoid, for radiation sterilization, materials that are APT or apt to fail. Then these include acetal, polypropylene, unstabilized polypropylene, or Teflon. Optimizing processing conditions also plays a major role in the successful sterilization of complex devices. Processing for conditions for E-beam and X-ray allow for greater control of sensitive materials, including continuous temperature control, split dose processing, and the use of intelligent tooling to distribute varying dose levels to different portions of the device. Another key parameter of irradiation sterilization is the dose uniformity ratio, or DUR. The DUR is the ratio between the maximum and minimum dose needed to effectively process a product. Particularly with E-beam sterilization, how the product is packaged, configured, and then oriented in the shipper box for routine sterilization is key to achieving an optimal DUR level. Also essential is examining how technologies such as modified atmospheres can aid in irradiation sterilization of certain products. And the use of antioxidant additives can significantly offset the effects of radiation. Modified atmosphere packaging trend is growing and it is most effective for radiation sterilization, where a package's atmosphere is infused with nitrogen along with antioxidants such as free radical scavengers to reduce the oxidation or ionization effects on plastics. For sensitive devices, stabilizers can be added to polymers to reduce harmful effects of irradiation on the product's mechanical properties and or physical appearance. Now, once the product is validated, has gone through the sterilization validation process, the quarterly dose audits are required every 3 months to ensure that the dose established for the device continues to efficiently sterilize the product and that there are no changes in bioburden levels, whether due to manufacturing or environmental conditions. 4 quarterly dose audits are required in the first year, and upon 4 successful quarterly dose audits, then a manufacturer may go to biannual dose audits. After 4 successful biannual dose audits, then a manufacturer is required only to perform 1 audit per year. The audits include bioburden as well as the sterility test, or as we have learned, the verification dose. And the dose audit requires 6 weeks to complete. Now, if a dose audit fails, then the sterilization dose can be augmented, but this is based on a number of positives, and this is an extremely complex process, and it invites higher level of scrutiny, whether by the FDA or your notified body. Then once bioburden is back under control and confirmed that the next quarterly dose audit, the normal dose levels can resume once bioburden levels are proven to be under control. And I would like to further illustrate the importance of working early on with your microbiology testing and sterilization contractor partners. And this could be no better illustrated by an actual example of a device manufacturer that is a customer of both NewTek and PBL. The device manufactured by this customer is an extremely sensitive device requiring low sterilization dose and a very tight dose distribution. We worked with this customer in designing optimized configuration for the processing of these devices in their shipper configuration, processing in a very tight dose range, as well as implementing a program of bioburden monitoring to ensure that the bioburden levels were under control and at the levels required to be able to validate the product at the low dose level needed in order to successfully sterilize this product. While during this monitoring procedure, we had found that while the overall bioburden results were in the range needed for processing of the device at the low dose levels required, we had seen unusual spikes in bioburden in just a small percentage of the devices, but this small percentage would have disallowed the low dose level that would have been required for successful sterilization of this particular device. So working on very closely upstream with this customer, Pacific Biolabs and NewTek, we devised a program in conjunction with this project became part of this company's Six Sigma program. And in working together, we developed a program to monitor bioburden at a component level. Through root cause analysis, we were able to identify that the source of the unusual spikes of bioburden was attributed to a manufacturer of a tape component used in this device. Once this cause of spikes in bioburden was identified, this company implemented upstream, extending to their suppliers a much more regimented program for clean room procedures that include capping and gowning, environmental monitoring of the clean rooms, that has led to this manufacturer of this, to be able to manufacture this device at a consistently low bioburden level. So I hope you enjoyed this little tidbit of a story, and as you are aware, controlling bioburden is key to successful sterilization of complex devices. And with this said, I will turn this presentation back over to Aaron, and he will address controlling bioburden or microorganisms in the manufacturing environment.
Excellent. Thank you, Jeff. Here you go, Aaron.
Thanks, Jeff. I think that that story really does kind of illustrate the case of, finding an issue and then having to kind of scramble to figure out what was actually going on. And the real important question is, how can we go ahead and then prevent events like in the case study? How do we prevent an issue before it upends our whole production process, kind of making us stop what we're doing, or worse, leads to an actual product recall? So the answer really is preparation and monitoring. I mean, as Jeff mentioned in that case study, kind of had to look at and actually look at all these different processes and find out where that issue was coming from. But we really want to kind of be prepared ahead of time and monitor everything. So you want to know as much as possible about your production environment and possible sources of contamination. And then put a plan in place to limit that contamination while monitoring and trending your bioburden to ensure that those steps are working. Or to put it more succinctly, an effective program to control microorganism levels in the manufacturing environment is essential to minimize the bioburden on the medical device being manufactured. Now, there are two main aspects to monitoring and trending bioburden: monitoring the manufacturing and production environment, called environmental monitoring, and monitoring your product bioburden. So looking at the environment allows you to gather data over time in your production environment as a whole. And by better understanding what is happening in the production environment, you're much better able to track down where an issue might have come from. Environmental monitoring then looks at many factors. It looks at air quality, water quality, and cleanliness of surfaces, for example. If one part changes, showing a higher microorganism level, this specific area can then be addressed. Bioburden studies are also used to monitor microorganism levels on materials that could affect the bioburden of the finished device, such as product components, manufacturing fluids, and product packaging. And this is illustrated in Jeff's case study, showing that it was a tape component that had that high bioburden level. So this bioburden data may provide useful information when investigating instances of high product bioburden levels or dose audit failures. Now we should also discuss bioburden spikes. So it may happen that most bioburden values are very near the mean, but occasionally a value may occur which is well above the mean, i.e. a bioburden spike. For instance, when performing a quarterly bioburden check on 10 devices, you may have 9 with very low bioburden and 1 with very high bioburden. These bioburden spikes are common in the medical device industry, especially when manual assembly is used in manufacturing. If bioburden data increase significantly or show extreme variability, the manufacturing process should be investigated so that corrective measures can be implemented. In order to know if your bioburden levels are changing in a potentially dangerous way, it can be useful to set alert levels or action limits for bioburden. An alert level is an established microbial or non-viable particle level giving early warning of potential drift from normal operating conditions. Now this is from PDA Technical Report number 13. Essentially, an alert level is set at some designated higher than normal level. It should be within safe or acceptable levels for your current sterilization level and program, but set such that if your bioburden hits the alert level, you know to investigate and address conditions to prevent further increases in bioburden levels. Setting an alert level is a proactive step. Now beyond alert levels are action levels. This is an established microbial or airborne particle level that, when exceeded, indicates a process is outside of its normal operating range. Action limits are set such that if bioburden readings go above this limit, you must take corrective action to address it, as bioburden above this level could definitely affect your product's sterility assurance level, leading to non-sterile product or a failed sterility dose audit. As I mentioned, information on these can be found in the PDA Technical Report number 13, as well as in ISO 11737, Section A 8.5. To summarize, changes in bioburden levels can alert you to a potential problem before it gets so large that it affects your sterility program. Monitoring our environment and bioburden levels is, of course, only half of what's necessary in an effective program. You also need measures in place to ensure that you are limiting and to controlling bioburden. It's likely that the most important aspect of this is your personnel and how they are trained. For medical devices, contamination resulting from human handling and contact makes up the bulk of bioburden. Two basic aspects of training are key to all production personnel. The first is personal hygiene and cleanliness. Small pieces of biological matter can easily be transferred from the human handler to a device, and so it's important to limit this possibility. The second key aspect is education on hazards. An effort should be made to educate all personnel about how important what they do is, and to educate them regarding what can happen in the event of a contaminated product, and the hazards potentially posed to humans using a contaminated product. This understanding should be clear to everyone who is involved in interacting in production steps. We can also limit bioburden through cleaning processes. This includes the cleaning program addressing production areas and surfaces, storage areas, as well as the production equipment itself. There should be a program in place to not only monitor these areas, but regularly clean them using cleaning agents. These agents are classified from weakest to strongest, starting with sanitizers, for example, isopropyl alcohol. The next strongest agents are disinfectants, phenols or 3% hydrogen peroxide, for example. And the strongest agents are sporicides, such as peracetic acid or acidified bleach. Some of these sporicides can be corrosive to equipment, so caution must be taken when using them. We can also limit bioburden through control of the device itself. Storage areas were mentioned above, and it's also important for a device assembled from components to look at the life and history of those components prior to assembly to see whether any steps may expose these components to potentially high levels of bioburden. This can understandably be difficult if you're working with one or more contract manufacturers or suppliers, and in those cases it may be necessary to regularly visit the facility or track component bioburden, as it is important to consider keeping a close eye on things. Finally, one last note on limiting bioburden, and I'll just touch on this briefly because this content itself could fill more than one webinar. Device design choices can have, in some cases, a significant effect on bioburden levels. For instance, adhesives can trap particulate matter, so selection and specific use can be critical. Small crevices or nooks can be hard to clean and can also attract or trap contaminants. And channels, for liquid flow for instance, can provide a safe area for microorganisms to gather and grow while also being difficult for a gas sterilant such as ethylene oxide to reach. Small crevices or nooks can be hard to clean and can also attract or trap contaminants. And channels, for liquid flow for instance, can provide a safe area for microorganisms to grow and gather while also being difficult for a gas sterilant such as ethylene oxide to reach. Of course, function of devices should direct form, but being aware of how specific forms can impact bioburden and subsequent sterilization may allow for small tweaks to improve cleanability or sterilizability. In summary, know your device bioburden. Bioburden levels affect your sterilization program, sometimes greatly. Now, bioburden must be monitored and tracked on a regular basis. Be aware and catch issues before they require corrective action. And monitoring, training, and controlling production areas are key. Finally, deliver safe and effective products to people that need them. Now, I want to thank everyone for your attention. I have a slide of references, and then Jeff and I are going to set aside a little bit of time to answer a few questions. We probably won't be able to take too many. We've I think, gone a little longer than we intended to. But again, thanks everyone, and I'm going to hand it over to Jeff.
Okay. Thank you, Aaron. Thank you, Jeff, for your expertise on these important topics. Before we move to the questions, I'd like to invite you all to visit these experts' websites, Pacific Biolabs and New Tech Corporation. Again, as Aaron mentioned, we're a little short on time for questions, but these gentlemen will be very free and open to answer your questions in a different format. So again, I'm going to turn this over to Jeff. Looks like we have one early question here related to Jeff, if there are so many advantages to using X-ray sterilization, why is it not widely used?
Well, that is an excellent question. And the reason is, even though X-ray technology as a sterilization modality has been around for over 50 years, the technology of E-beam X-ray uses E-beam accelerators. And the technology is now at the point where there is efficient use of energy to generate the power that is required for X-ray energy. So you will see X-ray used more often as it is a superior alternative to gamma. So basically, NewTek will be the first company within the United States to have X-ray sterilization. X-ray is covered by ISO 11137, and it is a matter, there's a lot of big companies, a lot of companies are interested in X-ray, but really nobody wants to be the first to validate their product via X-ray. So once that starts happening, you will see X-ray emerge as a well-known and preferred and attractive sterilization modality. Thank you for that great question. I think we're kind of running over our time allotment here.
Again, thank you everybody, and we hope to see you at one of our industry events, or again, feel free to contact these companies directly. Enjoy your day.